Welcome to lecture 27. So today we will continue with our discussion of Mercer's theorem, and the origin of this theory is basically David Hilbert's work on integral equation, and integral equation was used for lots of applications, for example mechanics or electromagnetics, even quantum theory. So he was studying a class of integral equations. So that class of integral equation, the integral operator, we have already defined. So the definition of the integral operator is this tk, and it is defined as k dot x fx dx. This is over the support of the kernel. So this kernel k, this is defined to be positive semi-definite, bounded, and these integrable as well. So these functions k dot x, this is L2. Okay. So in the last class it has been shown that this function, this operator tk is also let me see what I have. So in the last class it has been discussed that this tk is self-adjoint. So self-adjoint means all the eigenvalues are real. So today I am going to extend it to show that the eigenvalues are not only real but also they are non-negative. Okay. So for that I have to take help of this positive semi-definite. So till now I know that tk is self-adjoint. Okay. And this tk, since it is self-adjoint, that means the corresponding eigenvalues and eigenvectors. So tk is equal to, say, lambda I psi I. So lambda is the eigenvalue, psi I is the eigenvector, and there are like countable infinite number of them. So I is equal to 1, 2. Okay. So from the self-adjoint characteristics we know that these eigenvalues are all real and the eigenvectors are all orthonormal. So it creates a basis. Okay. Until now there is no need to define any reproducing kernel Hilbert space yet, because this integral operator is defined on L2 space for good. So L2 theory is fine. So what I am going to show that from this positive definiteness of k, I can show that these eigenvalues are not only real but also non-negative. Okay. So I start with this. So I can say this to be a lemma, that lambda i's are non-negative. I'm starting with this proof. So how will I start? I will show that lambda I inner product with psi I and psi I. Now we know inner product is linear to the first term, so it is lambda I psi I psi I. And psi I is basically norm of psi I square, which is positive, non-negative, we know. So this is equal to, now from the eigen equation I know this is tk psi I and psi I. So now I can write in terms of the integral. So the integral is of this form. So the outer integral is of this inner product, and the inner integral is basically for this tk. So over s, and this tk, this will become k. Let us write down that this is having some running variable y, which is basically the, now suppose this parameter is y of this one, and the running variable here is y. So this will become kyx psi ix dx. This is the inner integral for the integral operator, and then I have psi I star y, star is the complex conjugate dy. So this I can apply Fubini now. So this will become integral s and s. I can write s cross s. So this is kyx psi I x psi I star y dx dy. Now what is this? This is the integral form of the positive definite definition of positive semi-definite definition of the kernel, right? So positive semi-definite means in the kernel definition, what did I show? Let me show from the last. Okay, I'm writing again. So semi-definite means that this is true for like for any complex numbers Ci and Cj. So Ci Cj conjugate k Ti Tj, and these are two values within the support, and I is equal to 1 to n, j is equal to 1 to n. This will be greater than or equal to 0. So this is the generalized form of that. So where the sum is replaced by the integral. So there are like uncountably infinite number of these complex numbers, and this is the kernel. So this will be greater than or equal to 0. So what did it say? So this is the norm, which is greater than or equal to 0. So if it is non-trivial, then it is always positive. So if that is positive, then lambda I is greater than or equal to 0. And this is true for all I. Okay. So this is the first result, which tells that the eigenvalues are non-negative. So based on that, I can go to the Mercer's theorem, and this is one of the most remarkable theorem in the theory of integral equation, and at the first during the first 2 decades of the 20th century, you can say. So it is right now 100 years old, but its application is like ever expanding, and like for the sake of historical record, this was probably the only contribution of Mercer in his entire life of researcher, like only significant contribution. So you really do not need to have too many contributions to become like significant or noteworthy. So the applications today, what are the applications of whatever you are learning here, reproducing kernel Hilbert space and Mercer's theorem and KL expansion? The immediate like application is not only communication. Communication is definitely one application, but it can go to statistical learning theory. So on all those like support vector machines, principal component analysis, everything falls within this scope. So what there, I will tell you later when this detection theory is done, that detection theory is exactly same as the classification theory in pattern recognition or learning literature. So these are all same. So if you are learning something here, that will have applications, even some like new research, you can say. For example, those statistical learning theory research. So I am coming to the Mercer's theorem now. So Mercer's theorem, he really did not bother about reproducing kernel Hilbert space. He just told that if there is a positive semi-definite kernel, so suppose K is a positive semi-definite kernel, and it is having the characteristics we were discussing, like it is having Hermitian symmetry. So this is Hermitian, this is bounded, etc. Then I define Tk just the way I have defined earlier. So Tk is the integral operator, and Tk I can write again. So over S, so K dot x fx dx. So this is the integral operator, and it has the following decomposition. So Tk lambda I is equal to psi I is equal to lambda I psi I. So this is the eigen decomposition. Then Mercer's theorem is, then K has the following decomposition. Kxy is equal to say kyx conjugate is equal to summation lambda I psi I x conjugate psi I y, I is equal to 1 to infinity. Okay, so this is the theorem. So this cardinal function itself, it is entirely recoverable from the eigenfunctions and eigenvalues, and it is basically like limiting sum of some product terms. So this is remarkable, like how the eigenanalysis is connected with the kernel. And you got some glimpses during those Prolet-spheroidal discussion, but I could not really go that further because this theory, this rich theory was required for understanding that. So if you now go back there, you can like relate certain things. That's why I skipped various proofs in that Prolet-spheroidal analysis. But that analysis is kind of similar. Okay, so let us prove it. So I'm proving it in this way. This is my proof. Okay, I don't really like followed the notation of the original paper, but it's a little clumsy, so I made the proof in my own way. So this is my proof, and you try to follow. If there is any discrepancy, you let me know. Okay, if you don't understand anything. So this is not from any book. So tk f y. So here y is basically the like parameter. Okay, I'm writing y because I don't want to write dot, because otherwise there will be some notational difficulty, but you understand this is parameter. So this is equal to kyx fx dx, isn't it? And this like here I have written dot only. So this is the parameter, this is the running variable. That is understandable. Now this is equal to, now kyx, this I can write as ky of x, the function when you parameterize one factor, you make it constant, and that other one is the running variable. Now what is this? This is the definition of inner product, where of course fx in general can be complex, so I have to make conjugate. So I can write without, instead of conjugating here, what I can do, I can write it like this, ky and f conjugate. So that is fine. So this is our way of defining the integral operator. Okay, that operator tk. Now I write the eigenequation. Eigenequation is tk psi I y. Y is the parameter again, is lambda I psi I y. So again this is the parameter. Now since this tk is a tk is self-adjoint, this tk is self-adjoint, so your psi i's are orthonormal. Orthonormal means orthonormal, and it will span the space L2, right? So there are infinite of them, countable infinite of them, and also we know that from the positive semi-definite characteristics that the lambda i's are non-negative. So these are from the previous analysis. Now what I will do, I will write the Fourier series for, so if psi i's are basis, like orthonormal basis, in L2, and here I am talking about only the support S. So S can be real line also. Then the Fourier series is for any function f is as follows: fx is equal to summation, say, f hat j psi j x, j is equal to 1 to infinity, isn't it? So, and where the Fourier coefficient can be computed from the analysis equation, can be computed by the inner product of fx and this, isn't it? Now I take a special function, and that function is, so fx is any function within that space L2. So the special function I am taking, let us take special function, which is kyx. Okay, so kyx is basically k of yx, but I'm not writing like this because this is my parameter and this is my running variable. Okay, if so, then I can write a similar kind of Fourier series. So kyx is equal to, I can write as kyj hat psi j x, j is equal to 1 to infinity. That is the Fourier series. So what is the coefficient? The synthesis equation kyj hat. This is basically the inner product of ky with psi j, isn't it? Now what is this? This we have seen before, this kind of expression where you are writing inner product. Okay, so we have seen that tkfy is ky f star ky psi I. There is no star here, so I can put the star on the other side. So this is same as tk psi j star y, because y is the parameter over there, y is the parameter, so it is ky. X is the like variable within the integral of the inner product, so x does not go out, y goes out. So this is same as this. Now what is this? This I can write as like over there you are applying, so this is also some eigen function, so it will be lambda j y, isn't it? So this is a value I get. Now I will put this value in the other Fourier series expansion. So Fourier series expansion will become kyx is equal to, say, kyx is equal to, now I can write it in this form, that j is equal to 1 to infinity lambda j jx psi j star y. So this is kyx. I can get the kxy form also. So kxy form is nothing but kyj conjugate kyx conjugate. This is Hermitian, so that will be equal to lambda j psi j star x psi j y, j is equal to 1 to infinity. So this is what Mercer's theorem is. Okay, so but Mercer's theorem give us a problem, like problem in the sense that now we have to change the definition of inner product and norm in terms of the Fourier coefficients, which was not there if you do not have this kind of eigen expansion. So let me show you to get reproducing kernel Hilbert space, because right now whatever definition we know for Fourier from the Fourier series theory about like Plancherel's theorem, for example. So Plancherel's theorem is what? We know that Plancherel's theorem is for Fourier series is inner product of two functions f and g is basically sum of f I gi conjugate. That is what Plancherel's theorem is for the inner product. However, this will not give us reproducing kernel, so we have to make a specific like a new construction of the inner product and norm to get the reproducing characteristics. Now you may ask that how are you changing the definition of inner product and norm? To remind you again, when we started discussing, we gave too many examples of inner products and norms, so it is not unique definition. You define something, the inner product and norm, everything should have a characteristics which it should follow. For example, this inner product should be sesquilinear, that means linear in the first term, conjugate linear in the second term. It should be it is 0 only when they are orthogonal, etc., etc. These are the characteristics. So if you can have a different definition, it does not matter. Similarly with norm, the distance. So norm you can define as like Euclidean norm, you can define as L1 norm, you can define as L infinity norm. So there is no like unique way of defining these things. Only the thing is they should satisfy certain characteristics. So in this way, I will show you why the new definition of inner product is required, because the existing definition using the this Plancherel's theorem, that will not allow us to have the reproducing capability. So to get the reproducing capability, I am making a new definition. Just a minute, my ink is over. So what I will do, I will first write down the Plancherel relationship for two functions, say f and kx, and I will show you that it will not it will not be capable of generating the reproducing capability of the space. So to get RKHS, we need something more. So apply Plancherel here. F and say kx. So f and kx is basically summation fj hat and kxj hat for all j. This is Plancherel. Okay. Now what is kxj? We just derived the kxj. So kxj is kyj I written. So kxj is lambda j psi j star x. So it will be fj lambda j psi j star x. Okay. Sorry, this kx is, so this will be conjugate, so this will not be conjugate. Yeah, this is positive real number, no issue. So j is equal to 1 to infinity. So what is this? This is basically summation lambda j into fj psi j. J is equal to 1 to n. Now this does not give you the reproducing capability. Reproducing is basically fx. You have to get fx out of it. So it will be fx if you can get rid of this lambda j, the inner like eigenvalue. Then the remaining sum, if lambda j is equal to say 1, or if you can divide the entire thing by lambda j, then you will get only this. So that will give you fx. So to get the reproducing capability of the kernel, we define the inner product as so this is our modified Plancherel, we can say. So inner product I am defining to be fj gj star divided by lambda j. J is equal to 1 to n. So the norm will be similarly summation fj modulus square by lambda j. J is equal to 1 to infinity. So with this definition, you can ensure that this will become reproducing. So of course, f kx will give you summation fj psi j x. This is exactly the Fourier series of f. So this is fx. So I get my reproducing capability back. So this is the necessary condition for like a function to remain within the reproducing kernel Hilbert space. Okay. So with this, I'm stopping this Mercer's theorem. Of course, there are lots of application, and if you get to have a course on this statistical learning theory, you will learn this again. But I just introduced it for some applications. So now I'm going towards our like requirement, which is KL expansion, Kerr-Hunen-Loewe expansion. Okay. So if the cardinal function is real, then the Mercer's theorem says that the cardinal function can be expanded as, I can write over there. Okay. So for real, the requirement for conjugation is not there. So kxy will be simply this, simply lambda j psi j x psi j y. Now from this I am moving towards the significant result, which is called the Carr-Hunen-Loeb expansion. Here a little bit of small anecdote. There is a famous Indian polymath whose name is also there with this expansion. So if you look at new texts, you will get the three name in this expansion, which is called KKL. The Indian guy is called Kosambi. Actually his name comes first because he was the first guy to develop this particular expansion for noise processes. And I am requesting all of you to like just go and search about this Kosambi. There were two Kosambis, father and son. So father's name is Dharmananda Kosambi, son's name is Damodar Kosambi. Father was a professor of Pali literature, Pali language and Buddhist philosophy in Harvard University. He was a friend with Professor Norbert Wiener's father, and these two sons, Damodar Kosambi and Norbert Wiener, they were like contemporary and friends. Then Kosambi completed his PhD from the US. Then he came back to India after like a few small time in the US. So, and he taught at different places in India, starting from TIFR to Aligarh Muslim University to many other places. And he worked on a variety of topics, starting from mathematics like probability theory, functional analysis, to like solving this kind of noise, to statistics. And then his like interest drifted away from these mathematical topics, and he worked on say numismatist, and then like history. He was a Marxist historian as well. And then like philosophy, Buddhist literature, or like his father was a Buddhist like a scholar, so he inherited something. So he worked on a variety of domain, and his contribution, if you just go and search in Google, you will get to know that what kind of polymath he was. Nevertheless, let us come to the point. So I am not going into the original papers, so this is my way of interpreting this Carr-Hunen-Loeb expansion. So it says that suppose you have a random process xt. I'm coming to the random process, okay, and t is having a support, the same support s, okay, it can be real number, and these are L2 function, but for the time being I am taking it real valued L2 function. Complex valued, it will add some conjugation here and there, so that is trivial work. You can just try it out from this real analysis, okay. So this is a zero mean second order random process, second order stationary random process. So define the kernel function to be the covariance of xs and xt. So if that is real, then it will be simply expectation of xt and xs. Yeah, xs and xt, same thing. If there is these are real, if these are conjugate, then there will be Hermitian symmetry, so you have to put one of them to be conjugate. Okay, so then there are two statements. They are like opposite to each other, converse to each other. So the first one is that okay, before writing that, I am writing that then if psi I t for all I in the natural numbers and t in the support set be a set of orthonormal function, in L2, then if the following is satisfied, that is the integral over s k st psi jt dt is equal to lambda j psi js. So this is the eigen equation, you can say. So this is the eigen equation of the integral operator induced by the kernel, you can say. So of similar tk. Okay, so this is the integral operator working on psi j. So tk psi j s is equal to this. Okay, then choose. Now there is a difference. Till now it is exactly in the same setting as earlier, as Mercer's theorem. Now you choose a random variable. So this will be a random variable. Why? This xi j is equal to 1 by root over of lambda j integral over s, the support. Now I am performing a like random integral, stochastic integral xt psi jt dt. So what I am doing, I am basically taking the orthonormal, one of the orthonormal basis functions is psi j, and then I am projecting my random process on that. So this is the inner product basically. So this is a stochastic integral of one of the random process with a basis function. So you will get a random variable, right? You can visualize it in this way. So what you can think of that this random process is what? Random process is ensemble of sample functions, isn't it? This is random process. So this is the ensemble. Now what you can think that you are performing this integral, this inner product computation for each of the sample functions of the ensemble, and every inner product computation for every sample function is giving you a real number. Okay, that is giving you a real number. So that real number is basically the values this random variable will assume. So that is how you can visualize this. So this is a random variable. Then xt has the following expansion. Xt is equal to lim. Lim means limit in mean square, you know, L2 norm, summation root over of lambda j xi j psi j t. J is equal to say 1 to n. Now why this 1 by root over of lambda j here and root over of lambda j over there? Can we make this one and this only lambda j? We can, but what I want to do, I want to make these to have these random variables. This is a sequence of random variables. There are infinitely, countably infinitely many random variables. I want to make them having a particular kind of variance structure. Basically, I want to make their variance to be 1. So that's why this normalization. You will see that. Okay. So this is the expansion it has, and this is called a bi-orthogonal expansion. Why? First of all, these basis functions are orthogonal. Okay, these are the coefficients. This is a multiplier constant. This is a real number, positive real number. This is random variable. But what I am saying that these random variables are also orthogonal to all the random variables. So this generates a random sequence, right? You are getting a random variable for every j. J is equal to 1, j is equal to 2. So at every instance of time up to infinity, n tends to infinity, you are getting one random variable. I am saying that all these random variables are independent. Not only independent, they are independent and identically distributed random variable, IID. So you can see from the random process, you are projecting on these basis functions. What you are getting IID random variables, and you are expanding the random process itself based on those orthonormal basis functions whose coefficients are those IID random variables. This is remarkable, and I can like now grasp the entire random process. My random process will come down to a random sequence, and which are IID random variables. So essentially you are bringing everything to that single random variable whose distribution eventually you will know, and this is like IID, so you don't have to go for multivariation. This is univariate. So this is remarkable in that sense. Let me complete the statement. And these random variables xi j's, j is equal to 1 to infinity, are IID with mean 0 and variance 1. All of them for all j. Okay, this is the first statement, forward statement. Let me write down the second statement also. So the second statement is, conversely, if xt is equal to limit in mean square summation I is equal to 1 to n, say root over of lambda I xi I psi it, where psi i's are IID with mean 0 and variance 1, then kst psi jt dt is equal to lambda j psi js. So if and only if both the side it works. If this is true, then that is true. If that is true, then this is true. So it is basically just the opposite side. So if this is true, then this is true. The next form is just the opposite. So I will prove this, and then I will show you some examples, and the examples can be of Brownian motion and additive white Gaussian noise. So our interest is mostly additive white Gaussian noise, and you will see that how like beautiful the expansion will be for additive white Gaussian noise, and after that we can move towards direction theory. Okay, so let us prove this. The proof will be remarkable, and it will require Mercer's theorem. That's why we spend so much time over Mercer's theorem. So let us start the forward one. So I define proof, the forward one. I start with the definition psi j is equal to 1 by root over of lambda j integral over s xt psi jt dt. Okay, so I will show that the mean of that random variable is 0 and variance of that random variable is 1. Okay, that is the first step. So mean expectation of xi j. Here what is random? Random is only xt, everything else is deterministic. So again, understanding Fubini, so expectation is nothing but integration. So there will be integration here, that integration enters there. So it is essentially Fubini's theorem. Expectation of xt Now what is xt? Xt is 0 mean random process. So for all value of t, this is 0. So integral is 0. That's 0. So mean is done. Variance. So since mean is 0, variance is just this. Okay. Real. So I can show you covariance also. Yeah. I am showing starting from covariance, so you will understand that they are independent as well. So let us start from covariance side. Yeah, covariance is equal to 1 by root over of lambda I lambda j. There are two integrals. Actually, there will be three integrals. So I am taking the expectation inside. So it will be this over s and s expectation of xt and xs, and then you have this it and js dtds. That's the covariance. Now what is this? This is this expectation of xs xt is what? That is the kst, that is the kernel. So you get one expression, I'm separating it out. One is kernel kst phi I say sds, and then phi j sds and phi it dt. This remains out. So what is this? This is basically the eigen expression what has been already given. So eigen form is basically 1 by root over of lambda I lambda j over integral. So this is the eigen expression which will be lambda j psi j t, and this is psi I t dt. Lambda j goes out, so this will become lambda j by lambda I, and this becomes what? Lambda jt psi jt psi it dt. We know that these are orthonormal basis functions, so it generates a Kronecker delta. So this becomes a Kronecker delta ij. Kronecker delta is 1 when I is equal to j, 0 when I is not equal to j. So this equal to Kronecker delta as well, because when they are equal, 1 is equal to I is equal to j, then lambda I is equal to lambda j, this becomes 1, and when they are different, the entire thing is 0. So this equal to this. So I get covariance is equal to delta ij. That means obviously variance is E of j square is 1. So I get IIT. So this is second like wide sense stationary, so second order stationary, so it depends only mean on variance. Mean is 0 and they are independent, and variance is 1. So we get the first expression that these are IIT, independent and identically distributed random variable with mean 0 and variance 1. Okay. Now observe the following. Observe the inner product between xt, the random process, and the random variable. Okay. So this is basically this is not the random process. Basically, this is the random variable at t. This is t is equal to parameter. Yeah. And this inner product is basically the probabilistic inner product, you can say. So I am talking about the in the probability space. So expectation of xt and xi j. This is what I am talking about. So this is what? This is equal to, I can expand like this xi j from the previous expression which I assumed. So 1 by root over lambda j expectation of xt integral xs psi js ds. This I can write. So that is the expansion of the random variable. That is how you have chosen, isn't it? So now what I can do, I can put like this xtss together again Fubini. So this will be j integral, the integral goes out, and I have expectation of xt xs psi js ds. So what is this? This is the kernel kst. What is this? This is j and jt. So root over of lambda j psi jt. Okay. So I computed any random variable on the random process. So if you fix the time, it becomes a random variable with this like random variable which is you have computed from the process. Okay. Now with this result I can straight away go to the like big statement of the expansion of xt. So limited mean square means basically I have to show that the error variance goes to 0. Okay, so it is in L2, so variance basically. So hence I can say expectation of xt minus, what is the form? The form was this, summation j is equal to 1 to n root over of lambda j psi j t, this square. I have to show that this goes to 0 as n tends to infinity. So what is this? Let us expand. So this will be, this is quadratic expansion, so it will be expectation of xt square minus 2 expectation of xt into summation lambda j psi j t, j is equal to 1 to n, plus expectation of, this is square, so square means basically you have to take double summation. So double summation of, I am varying it from like in two terms, one is I and another is j. So this is over I is equal to 1 to n, this is over j is equal to 1 to n. So root over of lambda I lambda j psi I psi j and psi I t psi j t. So this is the form. Now expand. Yeah, follow this carefully. Okay. So this is a big expression, but like derivation, but not difficult. So this is equal to, the first one is expectation of xt square. Second is, now second is interesting because the noise goes, expectation goes only to xt and psi j. So summation to summation j is equal to 1 to n, expectation of sorry, there is first this root over of lambda j, then expectation of xt psi j, and then psi j t. Now this we have already computed a little while ago. So xt psi j, expectation of xt psi j is root over of lambda j psi j t. So that will come in the next line. I am writing already. Expectation of xt square minus 2 summation. So root over of lambda j and root over of lambda j will become lambda j, and you have t square. So this is what? J is equal to 1 to n. Okay. So psi j t basically. Plus what is there? Plus is this. So expectation goes inside. So it will become summation I is equal to 1 to n, j is equal to 1 to n, root over of lambda I lambda j, then expectation of I j psi I psi j. So there are how many terms? Total n square terms. But out of the n square terms, you see that this is expectation of psi I psi j is the Kronecker delta, isn't it? So this will become Kronecker delta. I is equal to 1 to n, j is equal to 1 to n, and this is root over of lambda I lambda j. This is Kronecker delta, and this is psi I t psi j t. So out of these n square terms, only n term survives where the Kronecker delta is 1. Everything else becomes 0 because this is 0, right? So where it will remain 1 when I is equal to j. So from the two sums, it will become one sum only. Xt square minus 2 sum lambda j psi j t square, j is equal to 1 to n, plus it also becomes one sum. Say j is equal to 1 to n. So lambda I is equal to lambda j. So I can write lambda j. So root over of lambda j square is lambda j. This is 1 and this is psi jt or psi jt square. So from these two, 1 goes, so it will become e of xt square minus summation lambda j psi j t square, or psi j I can write it to invoke Mercer's theorem now. So what was Mercer's theorem? Let me bring that formula. So it was what? So lambda j psi j for x and y is kxy. When they are the same argument t and t, it will become ktt. So it becomes ktt minus basically ktt. Now what is ktt? Ktt is the covariance of xt and xt. So yeah, that is in the limit. So as n tends to infinity. Okay. So I should write it as it is limiting case as n tends to infinity. So this is in the limit is ktt. So that is equal to e xt square, and this is ktt is covariance of xt with xt, that is nothing but e of xt square. So it is equal to 0. So that is what that is where Mercer theorems became handy. And not only that, to understand these integral equations and these eigenvalues and eigenvector, the entire analysis helped to develop towards this. Let me quickly show you the converse also. Converse is easy actually. So the converse side. So I know that xt is equal to limit in mean square n tends to infinity, I is equal to 1 to n, so root over of lambda I xi I psi I t. So then your kts or kst is equal to expectation of xt and xs. What is that? That is limit in mean square, two summations, one is I, another is j, root over of lambda I lambda j, psi I t psi j t, expectation of xi I xi j. So this was given, and what is given? That these are IID with mean 0 and variance 1. So this is basically Kronecker delta. So I get, similarly I get one sum, say I is equal to 1 to n lambda I psi I t psi j t, and this is like the Kronecker delta becomes 1. Okay, now I get it. KTS is equal to having this form, isn't it? So what is this? The integral equation. What is the converse expression? Right. What I am trying to prove. I am trying to prove the converse expression is this one. This integral equation is satisfied. So now I can do that because I have the form already. So integral over s k st it dt. I'll apply this form. Okay, so this will be equal to s summation lambda I psi I t over there it was s. Okay, sorry, it was s. It was s. Psi is. So psi it, psi is, and psi it dt. So clearly it will become summation, it is goes out, I is equal to 1 to n. So as n tends to infinity, obviously, so I is equal to 1 to n. So lambda I, say let me take this to be j, because this is the running variable, so this is suppose j. So lambda I, then psi I, psi is, then I am taking the integral inside which is over dt, so psi it psi jt dt. Now what is this? This is again like if this is Kronecker delta, so like this will make this is like this integral will have value only when I is equal to j. So finally what will I have? I will have only j. So lambda j psi js. This is what remains, and that is exactly what our integral equation is. You understand this step, right? This is a Kronecker delta. I am writing again. Lambda I psi is delta ij. I is equal to 1 to n. So this will become 1 when I is equal to j. So I becomes j. So only for I is equal to j, this will become 1. Everywhere for every other I it is 0. So j remains. So that's the KL expansion. Okay. So let me quickly give you one example that how beautiful it becomes when I take a particular like noise form. So let us take the noise form to be like additive white Gaussian noise. That will be better. Additive white Gaussian noise is called a generalized noise because its covariance function is not the regular covariance function. It is not L2. It is Dirac delta function. Nevertheless, let me first show that, because our example can be band limited noise. Okay. So for additive white Gaussian noise, covariance, the K function of say W, T and Ws, Xt and Nt and Ns, whatever, say Nt and Ns, which is K Ts, I can write, is Dirac delta. So N0 by 2 delta T minus S. This N0 by 2 is the power spectral density. So N0 by 2 is called the power spectral density. This 2 is historical significance. I can write N0 also, no issue. Power spectral density. So you can see that this is like if you take the Fourier transform of this covariance, you will get the power spectral density, which is a constant. So that makes sense, because you know that the Fourier transform of Dirac delta function is 1. Okay. Now KL expansion. What will KL expansion be? KL expansion will say that NT will be equal to LIM, limit in mean square, I is equal to 1 to n, root over of lambda I, xi I, psi it. Okay, I have to find out the psi its. Okay, so I have to basically solve the integral equation. So how to solve the integral equation? The integral equation will be, and also like this is the expansion, and our random variable will be the following: root over of lambda I integral nt psi it dt, or the inner product form, you can say. So this is the random variable which you will get, and this is the expansion. So for that I need first the integral equation. That integral equation, and solving that we will get the eigenvalues and eigenvectors. Okay, so let me write down that first. That is over the entire, here the noise process is defined over the entire real line. So minus infinity to infinity, kst psi I t dt is equal to lambda I psi is. That is what the integral equation is, isn't it? This is the like kernel integral operator, you can say, operator eigenequation. Put the value. So this will be n0 by 2, that is a constant, it goes out, delta t minus s psi I t dt is equal to lambda I psi I s. Now this is what? This is convolution, like s minus t is equal to t minus s, it does not matter. So this is basically the Dirac delta operator working on this. So what value you will get? You will get psi I s will be equal to lambda I psi I s. Now this is remarkable. So as long as psi I s is non-zero, non-trivial, you get lambda I is equal to n0 by 2, and that is true for all lambda, all I. So all the eigenvalues are same, that is n0 by 2. Okay, it makes sense because your power spectral density is flat and eigenvalues is nothing but spectra only. So what is eigenfunctions? This is arbitrary because there is no restriction here, right? This can be any arbitrary basis function. Orthonormal basis function. There is no restriction. So it can be pt minus kt as well, which is our orthonormal basis function for PAM demodulation, P or Q. This is the matched filter like receiver orthonormal basis function, isn't it? So this we will use in our demodulation and then going towards detection. But before going to detection theory, and what are the random variables then? So this is the expansion we got. So the random variables are IID random variables, and their mean is 0 and variance is 1. And what is the distribution? This is Gaussian, additive white Gaussian noise. So your NT is Gaussian, so definitely the distribution will be Gaussian. So I can clearly write the probability density function f of those random variables to be 1 by root over 2 pi to the power minus x square by 2. That's it. So sigma is equal to 1, mean is equal to 0. So I know exactly the density function of these random variables. This is easy for trivial, you can say, when you are talking about the entire real line as the time and the entire spectrum. But when for real applications, say digital communication, your entire spectrum is not there. So the noise will not be having infinite bandwidth. It will have some bandwidth. It is like white over a band. So then things will become different, and we will show you that then the kernel will not be delta, rather it will be sin C. And with sin C, these equations will be different. But before going there, I will give you one more example of, say, Brownian motion. Then you will see that all problems, all KL expansions are not this easy or this trivial. It can be a little tricky also. Okay? But that is the next class. Till then, bye.